All right, so some of the notes, some of the class notes are going to be a little redundant because I figured they were easy to forget, and so I wanted to go over some of the stuff more than once just to make sure yeah, it made sense last night in the video, but we're going to hit it twice so that it makes more sense today. Okay, so the notation that we learned yesterday was that limit notation. I keep using that pen and it keeps being dumb. So we're going to say the limit as n goes to infinity, and then remind me what that notation was. We talked about it yesterday and we did it in the video. Delta x times summation where I equals 1 to n of f of xi, or x sub I, okay? And then f of x sub I represented the height of the rectangle. What did delta x represent?
The change.
Yeah, the width of the rectangle. So we have infinitely many rectangles. When we said the upper boundary of the interval minus the lower boundary of the interval divided by how many subintervals we had, that helped us figure out how wide each rectangle would be, right? So the width, and then to figure out the height, we would plug that x-coordinate into the function. That would give us the y-coordinate, and the y-coordinate was the height of the rectangle. So this is to figure out the width and the height, and then we're doing the summation because we have a bunch of different rectangles we're adding together, right? And that's how we get the area under the curve. Okay, so to write this as an integral, we have a stretched out s for sum. Get it? It's like somebody was like, I don't want to draw this. Let's draw this instead. We're going to shorthand the shorthand. Isn't that nice?
I like
Yeah.
that.
What do I write for lower bound? A. A is the lower bound. What's the upper bound?
B.
B, because we say the interval from A to B. And then do you guys remember what comes next?
The integrand.
F of x dx, which is the integrand. And again, f of x is the height. And here, dx just means the change in x, right? D dx is the rate of change of x. And so this is the change of x, which is the width.
That's because delta literally means change.
Mm-hmm. So when we look at this, most students will remember always to put the height, but they will forget to put the width. And I forgot to make the poster for it, which I will do tonight, but that's going to be a dead baby animal, is if you forget to put the dx on the end. It is seemingly unimportant, but if you don't have it there, then all the mathematicians go, oh, why do you only have heights of a rectangle? Why no width? Yeah.
Should be a hamster.
I think it already is an animal, but I'll have to check.
Okay.
It might be a squirrel, which would be funny because that's pretty close. Yeah, that's pretty close.
It should be something that's really fat when it's a baby animal because of what it's with.
Oh, sure. That's fair. I
Fat
like that.
hamster.
I like
Yeah,
that.
we already have those.
All right. This is the what area under the curve?
Baby pig. Baby pig.
This is the
Area.
exact. It's not approximate anymore. When you have infinitely many rectangles, this is the exact area under the curve. It's a perfect answer. Okay, this is the exact area under the curve. All right, so say it again?
That's how you do circles. You get infinitely many shapes.
Yeah.
Rectangles.
Yeah.
compounded onto each
And you
other.
add them. Yep. So when we look at this notation right here, what is this trying to say?
From 0 to 4.
From 0 to 4.
Height
Height and width of the rectangle. So it means from 0 to 4, find the area under the curve. Now, we don't have to draw rectangles for that because we actually know what this shape is and how to find its area, right?
Semicircle.
It's a semicircle.
1/2 pi r squared.
1/2 pi times the radius squared times 2 squared.
So 2 pi.
2 pi. Okay, so this area right here is 2 pi. Okay. The area, if we look from 4 to 8, what shape is this from 4 to 8? Trapezoid. Does anyone remember the formula for area of a trapezoid?
You gotta turn it into
Base 1 plus base 2. What's the length of the first base? Or the top base? 1. What's the length of the bottom base? 4. So 1/2, 1 plus 4, times the height of the trapezoid, 2. So what's that area? 5. Okay. What about if we do from 8 to 12?
2 pi plus 5. Oh wait, no, that's not. That's the next one. Sorry.
8 to 12. 1/2 base times height, but it's underneath the x-axis.
The height is -2.
The height is -2. That's fair. Okay, 1/2 base is 4, height is -2. So what's the area?
-4.
-4. Okay. So if we're going to look at the area from 0 to 8, what should we do? Add what?
2 pi and 5.
2 pi plus 5. Those are not like terms, so that's as exact as I can get it. What about the area from 0 to 12?
You add all of the terms.
Add all of them.
-2 pi plus 5 are like terms. It's 2 pi plus 1.
2 pi plus 1. Okay. So sometimes when you're finding the area under the curve, you can truly break it up into shapes that you know, and then you can find the exact area and you don't have to use the rectangles. So when we are approaching problems, we're going to use the rectangles if they say approximate the area and we can't see a shape, or if they say use a Riemann sum, then we'll know that we're using the rectangles.
If anyone's curious, it's 11.28318 and 7.28318.
Thank you. She said insincerely. Moving on. All right, example 2. So we have this in the integral notation. They want us to write it as a limit of sums. So that means they want that limit notation with the summation in it. Okay, so how do we start that typically?
Limit as n goes to infinity.
Okay, so limit as n goes to infinity. And in the front, we need that delta x, right? And so for delta x, how do we calculate what that should be? 5 minus 1 over n. So we do the upper bounds minus the lower bound divided by n. So that's going to be 4 over n. And then we have our summation. I equals 1 to n. Okay, and then we need our x sub I, which is 4 over n times I plus 1. Does this remind you guys of anything?
I mean, the other Riemann sum stuff.
It should remind you of something from Algebra 1 or Math 1.
Oh, slope.
Slope. The change. This is kind of like the x-coordinate because it's what we're plugging in. We're plugging in 1, plugging in 2. This is your initial value. So it's y equals mx plus b. You guys see that?
Yes.
Oh, interesting. Okay. That might make it more memorable. Might make it easier instead of something you have to memorize. It's like, oh, let me think about the change. Keep it.
4 over n is just like n.
Yeah. It's your slope. Yeah. All right. So now we're going to say this is what we're plugging into the function. We got a crazy function here. So what should I start writing now?
4n plus I plus 1.
Or could you also just write f of...
We're going to do the worst case scenario because we know that f of xi is the easy, or f of this stuff is the easiest way to write it. So we're going to write it the hard way just so we have it in our notes. Yeah.
That's what I did. I was just wondering if you were given this problem.
Yeah, my guess is this would end up being a multiple choice problem as opposed to FRQ.
Okay.
And then FRQ would be where they would accept more answers, multiple choice, you gotta know. Yeah. So we have e to the x, then we have x squared, then we have minus cos x. And we're done.
Cool.
Yeah, super fun.
It's not very pretty.
No, it's pretty ugly looking. All right, the next one it has a limit of sums, and we need to express it as an integral.
S saw math meanwhile.
Nope. This is not the time. All right. What's my function?
You could
2x to the third plus ln x minus 4.
Yeah, so what I like to do is cross out the insides because then you can see where the x's are. So 2x to the third plus ln x minus 4. And if you think about how multiplying would work for a rectangle, we're going to have to put this in parentheses, 2x to the third plus ln x minus 4, because that's the height of the rectangle, and then dx is the width of the rectangle. So you would need that in parentheses because the dx technically goes to all of it. Okay. All right, and then we have to figure out what our lower bound is and what our upper bound is. You should be able to find the lower bound pretty easily. It's not -4, it's pi. Because if we remember, it's the number that you add on the end of what you plugged in. So pi is your a value. So that's our lower bound. So now we can say, if we remember where delta x came from, that was b minus a over n, right? And in the problem, b minus a over n simplifies to be pi over n.
so 2 pi.
So b minus a equals pi, or b minus pi equals pi. And then b equals 2 pi. So lower bound is pi, upper bound is 2 pi. So I'd say like the hardest thing to find is that lower bound, upper bound. The rest of it's not too bad. Okay. How do we feel about that part so far?
Pretty solid.
Yeah, not the most fun. I think when I do this, I'm like, I'm going to forget that as soon as my notes aren't in front of me. That's kind of how I feel about it. So we'll practice it a bit and hopefully get it in our brains. Okay. Oh, yeah. Mm-hmm. All right, go ahead and turn the page. So, properties of definite integrals. We're going to go through a bunch of these, and some of these are kind of obvious, and some of these you're going to have to make sure you write them on a cheat sheet, you use them, you have this paper out, because they're not as obvious, and they'll make a difference between you getting multiple choice questions right or wrong. So the first one is, if I have from A to B, if I were to flip this from B to A, that means I'm essentially finding the area, but I'm doing it backwards, which means that the area is going to end up being negative. So if I switch the boundaries to be opposite of what they're supposed to, it's going to make that area negative.
Okay, that makes sense so far.
Mm-hmm. If I look at the area from A to A, that's like an interval of nothing, right? So that's an area of 0. Okay. Now this one is saying we have an area of a rectangle. The height of the rectangle is C. The width of the rectangle is B minus A. So this is going to be C times B minus A. That's one that doesn't feel quite so obvious. It makes sense, but it doesn't feel quite so obvious. This is the one that people usually mess up or forget about or just don't do correctly. So that's a good one to remember. All right, this property says if you've got some sort of function and you've got a number in between, like this is the height of the rectangle and they're telling you to multiply that, like let's say we're finding the area and they're saying 3 sets of the same area. That's like what the C in the front would be. You can just take that coefficient and move it to the very front. So that would be C times the integral from A to B of f of x dx.
Are we going to use some examples of these?
Mm-hmm.
Wonderful.
I think like these two to me make the most sense. Some of the other ones we have to look at.
Just like a limit type thing.
Mm-hmm. All right, and then this one is saying if you have 2 different functions you're looking at, you can separate them. So the area of f of x dx plus the area of g of x dx. Oh yeah, plus or minus. The next one we already did. So this one is saying if you start with one interval, this was like the front of the page, we did from 0 to 4, and then we did from 4 to 8, and we just added the two areas together. So if you have one interval and another interval, you could just say from A to C, f of x dx. You can put them all together like that. Okay. So for example 4, we're actually going to use a combination of these properties. So I'm going to go ahead and I'm just going to split it up, and I'm going to call the 4 f of x and the 3x squared g of x. So I'm going to say the interval from 0 to 1 of 4 dx plus the interval from 0 to 1 of 3x squared dx. And with this one, I'm going to go ahead and take that 3 and move it to the front. So I'm going to say from 0 to 1, I'm going to put the 3 in the front, x squared dx. Okay, and then in that first video, we already approximated the area from 0 to 1 of x squared. Does anyone remember what that was? 1/3. Okay, so this second part is 3 being multiplied by an area of 1/3. So I took the coefficient, put it out in the front, and then I just said I have 3 sets of that area. Okay, over here I'm saying I have a rectangle, and that rectangle has a height of 4, and it's on the interval from 0 to 1. So I'm going to say for the first one 4 times 1 minus 0 to find that rectangle. And the reason that's okay is because this is a horizontal line, right? If I have y equals 4, that's a horizontal line, so that curve doesn't change. Using a rectangle to find the area underneath that curve is very appropriate. That would be a horizontal line on the interval from x is 0 to x is 1 with a height of 4. Okay, so if I multiply all that out, what do I end up getting? Yeah, 4 plus 1 equals 5.
So I get how to like use these equations. I'm just confused as to what the dx is.
The dx is the width of the rectangle. It is notation. It doesn't make a big difference for us.
So what would you plug in there?
You don't plug anything in there. It just sits there. It is mathematically the part of the notation that says, yep, I'm still thinking in terms of rectangles, infinitely many rectangles.
Later down the road, does it eventually?
Nope.
Never.
Just
Nope.
mathematicians are particularly bad.
Yep. It is that part of the notation that always reminds you where you started from. You started from rectangles, adding infinitely many of them. All right, example 5. So this says the area from 0 to 10 is 17. The area from 0 to 8 is 12. What's the area from 8 to 10? It'd be 5. It's pretty easy, right? So I'm going to go ahead and write out the notation so we can see exactly like what that should look like. So I'm going to say the area from 0 to 10 is the same thing as the area from 0 to 8 plus the area from 8 to 10. So the area from 0 to 10 is exactly the same as the area from 0 to 8 plus the area from 8 to 10. And then if we just think in terms of numbers, we have an area of 17 equals an area of 12 plus an area of question mark. And then what's our question mark? 5. And so then we can say, oh yeah, it's obvious the area from 8 to 10 should equal 5.